Physics World.
Hello, and welcome to this episode of the Physics World Weekly Podcast. I'm Hamish Johnston. This week, we're going to chat about the amazing quantum properties of diamond defects and meet the physicist who captained this year's championship-winning team on the BBC's University Challenge. Teledyne Hastings Instruments is proud to sponsor this podcast from Physics World. For over 75 years, Teledyne Hastings has provided reliable vacuum gauging and precision mass flow controllers and meters. We were trusted to help bring home the moon rocks. Let us help you with your toughest vacuum and flow applications. Visit us at teledyne-hi.com. Diamond is more than just a pretty gem. It has many attractive properties that stretch far beyond its aesthetic appeal. That's the opening line of a recent article in Physics World that was written by Matthew Markham and Daniel Twitchen. They are physicists at the company Element 6, which is based here in the UK, in Oxford. Their article explains how atomic-scale defects in a diamond lattice can be used to create a range of technologies, from qubits for quantum computers to sensors for medicine and navigation. I'm joined down the line from Oxford by Daniel Twitchen to talk about the remarkable properties of these diamond defects and how they are being put to work. Hi, Daniel.
Hi, Hamish.
So let's start with the basics. What exactly is an NV defect in diamond?
Okay, good starting question. There's really two parts to answering that question. The first is the diamond part, and then the second is the NV center. So firstly, over the last sort of 20 years, there's been lots of progress in how people can make diamond and engineer its properties by utilizing new techniques of growing diamond. And those techniques are largely called chemical vapor deposition. So we're growing diamond from a vapor phase, from a plasma, and in doing that, we can engineer its properties. And one of the things diamond, like many materials, it's often the impurities, the defects in the material that add the character, add the characteristics, makes it conducting, makes it colored. And one of those color centers in diamond, or one of those defect centers in diamond, is nitrogen vacancy defect. And in simple terms, we all remember from school, diamond has this four-fold coordinated tetrahedral lattice made up of carbon atoms. One of those carbon atoms is replaced with a nitrogen atom. Nitrogen, next to carbon on the periodic table, has a similar atomic radius to carbon. So basically, there's a very high solubility of nitrogen into the diamond lattice. And then one of the neighboring carbon atoms, that nitrogen atom, is replaced with a hole, a gap, a vacancy. And that's what we refer to as the nitrogen vacancy center in diamond. That nitrogen vacancy center, once formed, is very stable. You have to heat the diamond to more than 1800 degrees C to break it down. The vacancies might be introduced through the growth process and the nitrogen vacancy grown in, or more typically, after we've grown the diamond with nitrogen, we will add vacancies by hitting the diamond with high energy radiation to create those gaps. And those gaps under annealing will migrate to form the nitrogen vacancy center.
And so these things are really small then. Would it be right to say that there are only two atoms across in the diamond?
Correct. This is really as atomic level defect. So this nitrogen vacancy center occupies effectively just two lattice positions in the diamond lattice.
And what are some of the useful properties that these NV defects have?
So the first thing, which probably the wider public is aware of, is these nitrogen vacancy centers are the same things that make diamonds pink. So you might read about some of these famous pink diamonds, natural diamonds, and that pink color comes from these nitrogen vacancy centers. Well, that's of interest to the gem industry. For me, it's really about the spin properties of this nitrogen vacancy center, which makes it very interesting. And it's so in the world of quantum, and it's often an overused phrase these days, but quantum, the battle with quantum is really a battle between control and isolation. You want your quantum system to be isolated so it doesn't become classical. At the same time, you want to be able to write to it and read from it. You want control and readout characteristics in the same way you would have in a classical, say, semiconductor system. So this nitrogen vacancy center has associated with it a spin. And it's possible this spin has a triplet ground state. So it has 3 energy levels as ground state. And normally those energy levels will be just populated with a Boltzmann distribution. Depending on the temperature of the crystal, would depend on how many electrons are in the MS0 state, the ground state, or the 1 state. But by shining green light onto this diamond containing these NV centers, or really energy above a certain, light above a particular energy, typically in the green part of the spectrum, we can spin polarize this nitrogen vacancy center. So what does that mean? It means these electrons in these ground states get excited to optically excited states, and then they relax and they come back down and they emit light. Unique to the electronic energy levels of this nitrogen vacancy center is that when the electrons come back down from their excited state, they preferentially drop into the MS0 state, the ground state. So by shining green light on, we can spin polarize this nitrogen vacancy center. So effectively, we can drive all the electrons into the ground state. So if you like, a spin temperature of 0 Kelvin, while the bulk crystal can still be room temperature. So people refer to it as spin polarization, optical spin polarization, shining light on to manipulate the spins into this ground state. Now, normally with many other quantum systems, to get all your electrons into that ground state, you do that by paying the price of thermal energy. You basically have to cool them down to very low temperatures to get them all in that ground state. Diamond, and this nitrogen vacancy center in diamond, is, as far as I know, still unique in the solid state physics community, is you can spin polarize at room temperature and get those in that ground state. And once they're in that ground state, effectively in a quantum system, a quantum bit, your qubit, you can consider that as an up state. By applying an RF field, you can turn it from an up state to a down state. So you can now manipulate that quantum spin once you've polarized them all into one state. So effectively, you have this quantum bit you can initialize, and then you can manipulate to be in an up state or a down state at room temperature. And that's pretty special and pretty unique.
So the spin, essentially, you've got this quantum mechanical entity sitting there at room temperature, isolated from its surroundings by, I suppose, is it just a coincidence that the properties of the diamond are such that the spin doesn't interact with vibrations, for example, in the diamond lattice?
Really good question. So the first part of that, these electronic levels associated with the nitrogen vacancy is probably a freak of nature. The fact you get this spin polarization, and the fact we haven't seen that in many other centers, either in diamond or in other materials, is pretty unique to this center. But once we have initialized this quantum spin, so we have this qubit in this solid state host of diamond, then typically in the quantum world, you want it to stay quantum for as long as possible. And what people often refer to as the decoherence time, the average time it takes to go from this quantum state into a more classical state. What that means, you want it to be very isolated. In many materials like quantum dots, gallium arsenide, if I were to initiate my quantum spin there, the very fact that gallium and arsenide have nuclear spins. So you can imagine like 2 bar magnets interacting. So these nuclear spins, just because of thermal fluctuations, would be flip-flopping around, and through dipolar coupling will interact with the spin I care about and lead to decoherence. So the fact that the diamond lattice is made up of 99% of all the atoms in the diamond are spin 0. So there are no nuclear spins, or very few nuclear spins, to interfere with my quantum spin. So firstly, that decoherence mechanism isn't there, and that's again pretty unique to diamond. The second is thermal vibrations. Crystal vibrations is another way that interacts with quantum spins, quantum states. But because of diamond's mechanical properties, it's those stiff, short, tight bonds, the actual vibrational energy is such that it doesn't interact with spin. So again, you don't get phonon-driven decoherence mechanisms. And the last part, which the physicists will understand, Spins can also interact with orbital spins via the spin-orbit interaction. Again, that in diamond is very, very small. So you've got this solid-state system diamond, you've got this quantum spin, and this spin is pretty much isolated from the environment, which means it has very, very long decoherence times. People in Harvard have measured seconds or tens of seconds. So once you've initialized this state, it can stay effectively quantum for seconds. And in that time, you can do an awful lot of operations and manipulate it and get the benefits of what quantum gives you.
So you've got this spin. It's very isolated, but there are ways that it can be interacted with. And I suppose that takes me to my next question. What are some of the scientific and technological applications of these NV defects?
So, I explained at the beginning how we spin polarize, and repeating that process is how we actually read the spin out. So yes, we can initialize it. Yes, it's stable. And yes, then you can read it out, and effectively you read it out by the intensity of light it emits. So the first sort of area where, when we first got into this field more than 10 years ago, was really around fundamental physics understanding, the fact you can use this quantum system to explore great scientific problems. I mean, one of the more famous results in recent years was the work led by Professor Ron Hansen in Delft in the Netherlands, where we showed for the first time a true loophole-free test of Bell's inequality. And effectively what we did there, we had two diamonds separated by more than 1.4 kilometers, and photons coming from these NV centers, an NV center in each one of these diamonds, were entangled. And by doing an operation on one, we could then interpolate what's happening on the second and do a true loophole-free test of Bell's inequality. So while that was a great scientific interest, what's the technological interest there? Well, if we think about a quantum network, the concept of being able to share quantum information over the equivalent of the internet, how do we distribute quantum information? We can't use a classical amplifier like we do with photons today going down through fiber optics. So the idea is at the moment with a quantum network, you need to build an array of distributed entangled nodes. So for example, you'd have a diamond at each one of these nodes and effectively send your quantum information through this set of entangled nodes through the NV centers. That's still a longer term application, and really Professor Hansen's work in Delft is the leader there and has done some wonderful work in that over the last few years. The work in element 6 that we've been focused on more in recent times is using this spin as a magnetic sensor. So you can think of, in a way, this quantum spin is a little bit like a little bar magnet stuck in this diamond lattice. If I bring another bar magnet, an external field near that crystal, that bar magnet will feel the influence, and it might feel the influence on its size or the direction. And based on how much light I measure coming out of the diamond, I can determine the size of that external field. So this quantum spin, this nitrogen vacancy center, is basically a magnetometer. It is a magnetometer. And what's sort of we've been exploring, what's the attraction of it from a technological point of view, is firstly, it's very sensitive. So yes, superconducting quantum interference devices, SQUIDs, are still the most sensitive magnetometers out there, but they require higher overheads of things like cryogenic cooling, etc. This sensor is approaching picotesla per hertz sensitivity, so it's getting very competitive with SQUIDs, but you get it at room temperature. Secondly, it has a very high dynamic range. So what that means, it's really good at measuring very small fields and very big fields at the same time. So imagine an electric car where you really care about the current coming from your battery and you want to protect the electronics. And protecting the electronics means you need to be able to measure from microamps to kiloamps. You would really like one sensor that allows you that wide dynamic range. So measuring current draw from batteries is a simple example. One that we've talked more about in the last 12 months is work we've been doing with Lockheed Martin for GPS denied navigation. So as we all know, we all heavily rely on our GPS to navigate going from A to B. But the GPS signal is actually a relatively weak signal. It's quite easy to actually intercept or tell you you're in a different place to where you think you are. So lots of people have been interested in alternatives for navigation than GPS. There's obviously interest from a defense community. but also civilian. Imagine Amazon was delivering your package to your door by its drone. Now, GPS best will in the world is maybe only 3 or 4 meters accuracy. I'm sure you wouldn't like it if you came to your door and the package was in the other side of the road or in the middle of the road, just been run over. So how could you increase the local accuracy that makes sure that drone lands that parcel on your doorstep? So magnetic navigation has been interesting there. So the Lockheed work is despite what we learn at school, the Earth's magnetic field is not uniform. The Earth's magnetic field varies dramatically and a lot. And if you can map that variation and then measure it, you can then use the Earth's magnetic field to navigate. So Lockheed have shown, using some of our optimized diamond for their application, navigation by the Earth's magnetic field.
And Daniel, I understand that there are also medical applications of NV defects. What are some of those?
So I think probably for most of us, the most common use of magnetometers we might come across in medical sciences is MRI, magnetic resonance imaging. MRI is obviously a phenomenal technology and has led to many breakthroughs and many lives being saved. But ultimately, it only has about a cubic millimeter resolution. So you imagine chemical processes that lead to tumors, that lead to diseases, ultimately are operating on the micron scale. They're chemical processes. MRI does not have the capability, the spatial capability, to be able to look at and measure and map those processes. So the medical industry has been interesting to say, how could we keep sensitivity, but how could we increase the spatial resolution of magnetic sensing? And diamond, going back to the beginning, where Hamish, you pointed out that this is an atomic size defect. This nitrogen vacancy center is of the order of a nanometer across in dimensions. So that nanometer gives you ultimately incredible spatial information. So if you can get that NV center close to what you want to measure, not only have you got sensing capability, but you've got spatial sensing capability of the order of nanometers. So for the first time, you potentially have the ability not only to measure, but actually map out and characterize chemical processes happening on the micron and submicron scale. So people are interested in that for brain science. I mean, still very little is known about processes in the brain. So if you can build a series of sensors that map and characterize those electrical signals in the brain, and those signals are small, so it needs to be sensitive, and obviously operate on a small length scale, so you need that spatial sensitivity as well. So brain science has been one area that people have been working on using these sensors. Another is heart, actually mapping the electrical signals in the heart. Companies in the UK with some UK academics have been looking at that as another use of this diamond magnetometer.
And I think I know on Physics World we've had some stories about using defects, to do NMR experiments. I think looking, for example, at the presence of tiny numbers of nuclei in a sample, and sort of mapping them out spatially. Is that is that an application that you see materials related?
Yes. Yeah, and there's been a couple of different approaches on using diamond for that, but one is effectively a two-dimensional array of nitrogen vacancy centers. So in a way, I talked earlier about how we grow the diamond. It's basically a two-dimensional growth process. So by growing it two-dimensional, we can create a layer of these magnetic sensors. So then you can potentially put a biological sample on the top of this diamond crystal and then actually image those processes and characterize them. I mean, particularly interested is the proteins that are signatures of things like brain damage or Alzheimer's. And typical techniques at the moment are not particularly sensitive to pick up those. So if you could offer a fast, quick way of detecting these proteins that allow more corrective medicine much earlier than when brain damage shows itself or Alzheimer's shows itself, is often too late. There's a great deal of interest there. In the NMR community, so linked to MRI, which I talked about, there's I talked about the challenges of that, spatial resolution, how long it takes to get a measurement. Anybody who's unfortunately had to have an MRI scan knows it's a pretty unpleasant 30 minutes of lots of noises and bangs, and you can't move a lot. If you could collect that data much faster, and obviously there's benefits in reducing cost, there's benefits for the patient. So these NMR, these nitrogen vacancy sensors in Diamond, you can spin polarize them and use them to enhance the spin polarization of the thing that they use to label the tissues in your body. So there's some lovely work from a company in Germany called Envision, who are using Diamond to enhance that spin polarization to improve NMR imaging.
Now, you mentioned that there are a number of different factors that come together almost miraculously to make these NV defects in Diamond very useful. But are there other defects in Diamond or indeed other crystals that could also prove useful?
Yeah. So in a way, this is almost the start of the story for me on a personal level. 20 years ago, I was working as a young academic in Oxford studying defects in wide bandgap semiconductors, and one of those materials was diamond. And diamond was particularly interesting because there's more than 500 characterized defect centers in the material, of which only very few do we really fully understand. So I was using things like magnetic resonance techniques and optical absorption techniques to try and probe these defects to understand why they made diamond blue, why they made diamond conducting or not conducting, why they made silicon carbide look like this or not like that. So first and foremost, for young academics and research students out there, there's still a tremendous wealth of things that we still don't understand in diamond. And as I said, there's more than 500 defects, of which perhaps only less than 10 we really understand in detail. And again, diamond's not uncommon in that. Silicon carbide is similar, silicon is similar. Again, silicon, the whole of our semiconductor industry is based on, again, the ability to dope silicon, to put a impurity in the material that changes electrical properties. Diamond is similar to that. So there's still plenty of opportunity and work in this area to come.
And what sort of capabilities does Element 6 have for developing diamonds for NV applications?
So at the heart of Element 6, we're a materials company. We've been around for 70 years now, and pretty much from beginning to now, our DNA is developing and growing synthetic diamond for new applications. Applications I work on, and quantum is one area, and I'll come back to. But we make diamond for acoustic elements, for speakers. We make diamond for electrodes, for sterilizing, for cleaning things. Diamond is very good at conducting heat. It's the best conductor of heat of any material. So if you've got a high-end electrical processor and you want to cool it, the ultimate thing to cool it on is to mount it on a piece of diamond. So Element 6 at its heart is about growing and engineering extreme materials. And within our framework of materials, it's diamond, it's cubic boron nitride, and it's tungsten carbide, of which most of my work is around diamond. And that means developing the growth processes for doing it, how we grow diamond. And we typically have two ways of growing diamond. One is high pressure, high temperature, which simulates how the earth grows diamonds, putting graphite under high temperatures and pressures. And the second is really what most of what I've talked about today. One of the outcomes of that is chemical vapor deposition. But growing the diamond is only one thing. I mean, growing a lump of stuff is great, but it doesn't really make any money. So how do you make money? Well, you make money by understanding and engineering and make it reproducible, by understanding how you can change the growth process to impact its properties to solve somebody's problems. So if you want to make an electrode, a robust electrode that doesn't dissolve in acids, I need to make a diamond conducting. So how do I do that? I might add an impurity into the growth process that makes it conducting. But then after that, I need to be able to measure it. I need to characterize it. So the heart of E6 is growing stuff, but then also how do I characterize it? Because we need to be able to measure these extreme properties. And often a lot of the research is not maybe just about how we grow it, but actually how we make that measurement. And the third, and that's absolutely critical part to it, is who we work with in partnership. Because we're a material. To solve a problem, we have to add technology. And typically, diamond is always, it's a step change solution. I wish we had, but we've never found a simple drop-in replacement. Today they're using X, tomorrow they're using diamond. Diamond's always found its place where it's brought the partner a disruptive opportunity, a laser that emits more power than ever before, a magnetic sensor that gives not only sensitive information, but a spatial resolution 1,000 times better than anything else. So working in partnership with other businesses to develop bespoke, unique, disruptive technology is, if you like, the third core part of the DNA of E6.
And you mentioned chemical vapor deposition as a technique that you use. Does that mean that that your process for making diamond, is it compatible to a certain extent with silicon process or compound semiconductor processes? So you can actually integrate these diamonds with NV defects into into chips.
That's a fantastic question. So yes, it's integral in the sense that it's a wafer scale process. So when we're growing this diamond, we're not growing small single diamond at a time. We can grow diamond up to deposition areas of 140, 150 millimeters. So it's a true wafer scale technology. Yes, it occurs in semiconductor equipment, very similar to what you'd see other materials like silicon carbide grown in. The one challenge is the chemistry to grow this diamond. At the part of the phase diagram where you wouldn't necessarily expect diamond to be grown, we have to produce an awful lot of atomic hydrogen. So the plasmas that we grow this diamond from obviously contain carbon, and typically we use methane there. But the magic is hydrogen. So we basically create a very hot plasma by pumping a lot of energy into a mixed gas of methane and hydrogen. The carbon precipitates out on a much cooler substrate around 1,000 Kelvin. And that carbon coming out comes down both as graphite and as diamond. But because I've got so much atomic hydrogen, the atomic hydrogen etches away the graphite, leaving behind, by default, diamond. And for 30, 40 years, nobody believed that this was a technique you could use for growing diamond. But it was actually some work that was rediscovered in Japan, some early work from the US and in Russia that Japanese was discovered in the early 80s, and we then entered in the late 80s. They actually said, yes, you could do this. So yes, it's a wafer scale technique. The challenge actually is that hydrogen. To be able to grow good quality diamond, you need a substrate which is tolerable to very high energetic flux of hydrogen. And typically that means there's only some materials you can deposit diamond on. As it happens, silicon is a good substrate. You can grow diamond on silicon. But all the other wire connects, electrical factors that might be there in a semiconductor device will be degraded in that plasma. So at the moment, we still haven't really found a way of solving that other than to do it in a classic flip chip way, where we make the diamond, we've got the silicon device, and then you put the two together. It's nowhere near as easy as that, but at the minute, we haven't managed to integrate those two, and probably, at least for the foreseeable future, is finding a way of integrating them external to the growth process is key.
Well, that's really fascinating, Daniel. You can read the article written by Daniel and Matthew Markham on the Physics World website. It's called The Diamond Quantum Revolution. Thanks for being on the Physics World Weekly podcast, Daniel.
Thanks, Hamish.
I'm guessing that some listeners here in the UK have fantasized about captaining a championship-winning team on University Challenge. This is a long-running and popular BBC TV program that pits teams from different universities against each other in a quiz. In some years, team captains have become celebrities, and some captains have even gone on to present programs of their own. This year's winning team was from Imperial College London and was captained by the physicist Caleb Rich. In the upcoming clip, Caleb talks to Physics World's Mateen Durrani about what it was like to win this year's championship. And he previews a special quiz about quantum physics that he has written for us. Caleb also gives his tips about how to write a top-notch quiz.
I'm delighted to be joined by Caleb Rich from Imperial College. Hi, Caleb.
Hello.
So let's start. You're a PhD student at Imperial College. Before we get into your quiz exploits, do you want to just tell us briefly what you're doing there?
So I work on the laser cooling of molecules. So basically we use Doppler cooling and other laser cooling techniques to cool molecules down to then look at their quantum properties. And specifically I'm looking at sympathetic cooling of molecules with atoms to try and create molecular quantum gases.
Right, and you're in which year of your PhD are you in at the moment?
I'm in my first year, but I did a CDT, so I've just finished last year. I was doing my master's project in the same lab.
Okay, so how did you end up? I mean, obviously you were the captain of the Imperial College University Challenge team. How did you end up on that program? How did you end up captaining the winning team in that competition?
Well, I went along to the first round of the selection, which is a written test. And there were about 30 or 40 people there that day, but there were a few different ones going on at different times so that people could make them. And I did pretty well in that, so I was invited back for a second round of selection where we were on buzzers, and it was sort of simulating the kind of situation of actually being on the show where questions are read out, we buzz in, and I did pretty well in that as well. And so they selected me to be captain because they thought that my communication skills with the team, the other people who I was working with, who then got picked during that stage, was good.
I mean, were you expecting to win the series? I mean, it must have been. What was your reaction when you won?
Well, yeah. So I was relieved and elated. Yeah, I mean, it has been a culmination of quite a lot of work, and in that, I've tried to go on the show a few times in my undergrad. Never quite got on, but managed to do it this time, and with a great team. And it was lucky we had such a great team that we could have a good chance of winning it.
So in terms of the preparation, do you actually do a lot of revision? Do you do homework? Do you read the whole of Wikipedia? What's your preparation tactics for being on the quiz?
Well, we had a few different things. I mean, as a team, we met up and we watched the previous series together as if we were in the show, like playing along and like buzzing for questions. And that gave us kind of a good idea of what everyone's on the team's strength was. And then individually, yeah, we did try and learn a few things. We split up into kind of specific categories that we wanted to focus on, each of us. Me, myself, yeah, I read a lot of Wikipedia. I often find myself going down Wikipedia rabbit holes. So that was all part of the preparation.
So what particular areas of expertise were yours, and what were your weaknesses? What topics did you fear would come up?
Well, for me, I mean, obviously physics has got to be a strength. I'm pretty good at modern history as well, music. I mean, me in particular, I'm no good at sport, and then maybe arc is my second worst one. So those are the ones I was hoping that I didn't have to answer anything about. But luckily, we as a team we complemented each other's areas quite well, I think.
But did you ever have a fear with the physics questions that you might get them wrong, because that would be quite embarrassing if you didn't get them right?
Absolutely, yeah. I was very worried that there would be a physics question I definitely should know the answer to, but couldn't quite get it. Luckily, that didn't happen.
So what was the hardest question that you faced, or what was the one that you felt most proud of sort of digging out of the recesses of your mind?
I was quite proud with, in the final, one of the questions was on non-Newtonian fluids, and the answer was oobleck. And I'd completely forgotten that I knew that as a fact, but it just came into my head. I mean, I've done those experiments in the past where you like mix. It's a mixture of corn flour and water that is like acts as a non-Newtonian fluid. And I'd made some with some friends during university as just like an experiment. And I found out that it was called oobleck. Yeah, it just came to the front. But I was scared that it was going to be the wrong answer because it's quite an unusual thing to say.
But I also read there was an article in the Sunday Times, of all places, about the fact that you're quite a keen quizzer yourself. So what's your advice if someone wants to set a really good quiz?
Well, I mean, so you have to always be on the lookout for interesting facts. I mean, a good quiz question is something you want to know the answer to. You're like, oh, that's a really interesting question. Like, what could it possibly be? I mean, you don't want any questions which no one really cares what the answer is about it.
So you set them for your pub team,
I do,
don't you?
yeah, I do. I run a pub quiz in Lewisham.
But that's presumably not just on science, that's on everything.
Yeah, it is, yeah. I mean, there's great resources out there. There's Wikipedia, which is useful for setting questions. There's loads of questions out there. I mean, you generally want to try and make your own or like adapt them in new ways. But there are lots of resources out there that can help you.
So you very kindly agreed to write a Physics World quiz all about quantum physics. That's going to come out later this week. I'm going to put myself in the embarrassing position of asking you to ask me one of your questions. Have you got one up your sleeve you can ask me?
Yeah, I think so. So, founding figure of quantum mechanics, Niels Bohr, was gifted a house by which brewing company? It was next door to the brewery and was connected to it by a pipeline providing free beer. Yeah, Carlsberg.
Carlsberg. I knew that one because I've been there. Whee, 1 out of 1. We'll save the other ones for the quiz on the rest of the week. Are they? How many have you got altogether? How many questions?
Well, you said 10. I'm currently writing them. I think I've got like 8 at the moment.
So I won't spoil it for listeners by asking you to ask me anymore. But wow, 1 out of 1. I feel quite pleased with that. So do you think you've got any more quizzes you're going to enter? You're going to be, because there is a whole world out there of sort of quiz people. It's a kind of professional sport almost. Do you plan to do any more of that?
Yeah, I think I do. I'm quite enjoying running pub quizzes and going to pub quizzes at the moment. I think I might get involved again, and there is an Imperial Quiz Society, and they do competitions against other universities and things like that, and other fun events. So I think I might get involved in that again.
And apart from University Challenge, do you watch any other TV quizzes? What's your favourite?
I mean, so University Challenge is obviously my favourite, but I think Only Connect as well is really interesting. It's actually so hard, and I have real respect for the people who go on it because some of the questions are just so hard.
All right, I think I'll stick with Beat the Chasers.
That is a good one as well.
All right, well, it's lovely to talk to you, Caleb, and congratulations from all of us at Physics World for winning University Challenge. And as I mentioned, your quiz will be on the Physics World website later this week. So thanks for doing that for us, and I encourage listeners to have a go at that.
Thank you. No problem.
That was Caleb Rich in conversation with Mateen Durrani. Caleb's quiz can be found on the Physics World website. I'm afraid that's all the time we have for this week's podcast. Thanks to Daniel Twitchen, Caleb Rich, and Mateen Durrani for joining me today. And a special thanks to our producer, Callum Jelf. This podcast was brought to you by Teledyne Hastings Instruments. If you like what you've heard this week, you can subscribe to the Physics World Weekly podcast via Apple Podcasts, or indeed another podcast app of your choice. Thank you for listening, and please do join us again next week.
Physics World.